And I think everybody has mentioned that as you feed the fish, they do something. They produce solids, or they consume oxygen, the oxygen consumption rate that David just went through in great detail, and how there's a lot of uncertainty there with oxygen consumption rate. It's a problem because, sizing systems, you don't want to oversize things and then the capital becomes too much and then you're selling stock. Anyway, so that's a real problem. But what we don't have a lot of uncertainty about is carbon dioxide. Fish respire and they produce oxygen, or consume oxygen and produce CO2 on a molar basis, as Mike mentioned earlier. So I'll quickly cover that production concept and then go through the rest of the presentation, talking about why CO2 is a problem, what complicates CO2. It's part of the carbonate system. We'll cover that and how that works. And then we'll talk about actual processes to degas, or to manage the gas of dissolved carbon dioxide in the water. And RAS is a controlled environment for anything, so salt water, cold water, warm water. We'll talk a little bit about how those different water quality parameters affect CO2 stripping, as well as the environment inside the building. So this is, as Mike Timmons mentioned, for every mole of carbon dioxide of oxygen that is consumed, you produce 1 mole of CO2. So it's just 1 molar exchange, whether it's across gills or what. On a mass basis, that turns to be 1.38 grams of CO2 produced for every gram of oxygen consumed. And if you were here earlier this morning, you heard that is really just the ratio of the molecular weight. So molecular weight of CO2 is 44, and oxygen is 32, and 1.38 is the ratio of those two. So for every mole, you have 1 mole of CO2 produced, and on a mass basis, it's 1.38 times the oxygen consumed. I want to tie this back to the mass balance. I'm not going to go through mass balances in this presentation, but show you kind of again repeating this, because it takes us, they say, hey, you have to repeat it, maybe David can tell you how many times to repeat it for your students get it. They say it's like 10 times before they get it, right? So we're repeating it a few times here. This is the word equation for mass balance on carbon dioxide. What was going into the control volume of the tank is the flow rate, the makeup flow rate times the concentration of CO2 in the makeup. That's the CMQ. And then what the fish produced, and that's going to be based on what you feed the fish. Then there's also what's leading the entire system, the makeup flow rate times whatever was in the tank, C sub E, concentration of CO2 in the tank. And then what your unit process removes. And so I've rearranged the equation so it kind of fits this CO2. The recycle flow rate, Q sub R, times the change in concentration across the unit process. So that's what comes out of the fish tank, we call it C sub E, so dissolved concentration of CO2 in the fish tank, C sub E, minus what comes out of the process that removes it, so C sub R. So that's a lower value. So that's the word equation, and they also the variables that we have been using really throughout the presentations today. And the P is really important, because you have to account for the amount of CO2 that the fish produce, or it could be anything consuming oxygen that they're producing, in order to solve this equation for the recycle flow rate, which is what we're showing at the very bottom. And this actually goes right on what Dave was presenting. So I also use OCR, oxygen consumption rate, to express how much oxygen is being consumed in a system. I typically think about it as a system. 100 kilos of feed per day is just for the example. But you can see 100 kilos of feed per day times 0.4 kilos of oxygen per kilo of feed fed. So I'm able to cancel out kilos of feed fed and kilos of feed fed. And I'm left with kilos of oxygen times the mass conversion of oxygen that is produced as CO2. So 1.38 kilos of CO2 produced per kilo of oxygen consumed. So Again, my kilos of oxygen will then cancel out. I'll be left with kilos of CO2 produced, in this case, per day. And when engineers like this 100 kilos of feed example, because you get these nice numbers. So in this case, the produced CO2 for the example is 55 kilos of CO2 per day. And typically when I'm doing mass balances, I'm actually doing milligrams per minute. It just happens to work out for concentrations in milligrams per liter. So it's important that we are able to establish the feeding rate based on bioprogramming and fish size and all those things we've heard from earlier today, especially when Ed was talking about feed loading. And then able to use some of these feed demand factors like oxygen consumption and CO2 produced to get to a P that you can go into the mass balance and then solve for the recycle flow rate. Right? And then once you have the recycle flow rate, you can start to design devices and compare devices and look at the cost of various things based on the efficiencies from data from the manufacturers. And if you don't take care of addressing the carbon dioxide that is produced in the system, what happens? Well, in the case of finfish, there are these well-known effects, the Bohr and the root effect. The Bohr effect is when elevated carbon dioxide levels decrease the ability of hemoglobin to transport oxygen. So hemoglobin, of course, is moving oxygen around in the blood. And when you have this elevated CO2, it affects that capacity to transport oxygen. And then somewhat related is the root effect. The elevated CO2 levels will also decrease the maximum oxygen binding capacity of the blood. Right? So I'm not a physiologist. I just know that high CO2 is bad. Right? So, and every species and every system, the tolerance for CO2 is different. Well, at least we thought so, and I'm sure it's still true, but more and more I spend time in the industry, I guess 30 years now, these numbers seem to be all pretty low. We used to think that some species could handle higher levels of carbon dioxide, like tilapia. When I was Mike's student in the 90s, we used to say, oh, a tilapia could handle CO2 levels of 40 milligrams per liter at max feeding. Right? I don't believe that's the case anymore. And even some of these values that we've developed at the Freshwater Institute for Atlantic salmon, they're dependent on water quality. So if you're in a very soft water situation like Norway is, or British Columbia is for their salmon, raising smolt or post-smolt grass, you wouldn't want the CO2 to build up in the grass to really over 10 milligrams per liter, because the softer water has an effect on the fish physiology, and they do not tolerate the CO2 as well. As opposed to where we are at the Institute, we have hard water, like 250 milligrams per liter hardness, and very high alkalinity, and that changes the fish's blood buffering capacity. And so our studies, Dr. Chris Good, Dr. John Davidson are in the room, or they were anyways. I'm their boss, I hope they are. Anyways, they've published extensively on trout and salmon CO2 levels, and in our water, it shows that 20 milligrams per liter really doesn't have an effect, right, Chris, on production, right? 10 versus 20 were the studies. So. But in Norway, those studies would show an effect. So it's important that you get with your biologist or your physiologist to determine what is the maximum CO2 you want to accommodate or allow in the system, and then you can design based on that. And that's what I was saying, C sub E. That's the concentration of dissolved carbon dioxide at max that's in the fish tank or the shrimp tank, right? So, and I see Robbins here. I know nothing about CO2 for shrimp, Robbins. That could be a problem, but we'll see. We're running some trials with the problem. So, what complicates carbon dioxide is that it's actually part of a natural water chemistry system called the carbonate system. And that has four main species, dissolved carbon dioxide, but then the hydrated CO2 is called carbonic acid, it's a weak acid. Bicarbonate